Hello everyone, welcome to lecture 19. Lecture 19 is about failure modes of reinforced soil, and this is from the chapter 18 of our textbook. The learning objectives of this lecture is to examine various modes of failure that is possible in reinforced earth structure or the reinforced earth wall. And the second is to understand the design procedure including backfill selection and to check up the external and internal stability. And by overviewing these two contents, we'll be prepared to continue to some examples for the external and internal stability analysis, which will be done in the classroom, in the class. Okay, let's move on. So the basic design philosophy is there are two big thinking or the thoughts. One is to limit the state failure. So here is called the failure control. So the concept is that we don't want to have the failure for this structure. And the second concept is performance-based design. So here we'll allow some deformation, but we don't allow the certain deformation exceeding this value. Right? So let's say that we have a soil and there's a vertical load from the upper structure, Q, and there's a lateral force by the retaining wall or some wall, and this is the reinforcement. Right? Then this reinforced soil is considered as a composite body. So there's a soil and there's a reinforcement. So overall stability is, first is the external stability issue, like the overturning of this wall, right? Or there could be some slippage, right? Or there's some bearing capacity failure like this, right? Because of this Q. And that's the first issue. And the second is the internal stability of this reinforced material. So if this tie bag is too tight, then there could be some rupture at the joint here, right? The connection between the wall and the reinforcement, or this strip can be just broken at the in the middle, right? Or this can be just pulled out, right? Just pulled out when there's active pressure, right? Which is called a slippage failure. So we're gonna see these the different modes of failure in the handout. Okay, so failure mode generally grouped into two. One is the external failure mode, and the second is the internal failure mode. So in the external failure mode, a case when the major failure plane considered lies outside the reinforced earth mass. And this type of failure mode is analyzed following the conventional soil engineering practices. And the common forms of the external failures are the one is deep-seated failure. And this deep-seated failure could result from poor backfill material and soft foundation strata. And methods for this failure mode is conventionally like slope analysis using some methods of slices. And the second is the bearing capacity failure. So this bearing failure can take place when the soil directly underlying the basement of the reinforced soil wall is of low strength. Usually Hansen's formula is employed to analyze such failure modes, just like the foundation design. So similar to especially the shallow foundation. Shallow foundation. And sliding, the third type is the sliding. Sliding is a type of failure one, which the reinforced soil mass slides, and usually the base of the reinforced block of the soil is placed at some depth below the ground surface, at the toe so that some passive resistance may contribute for stability. Such failure modes are treated in the same manner as a retaining wall. So this means that generally you have some depth right here, and this gives you some resistance against the sliding failure, right? Because you have some force by this from to this direction, kind of a passive force. So that means that here at the toe, some passive resistance contributes for the stability, so it increases some stability. And the last is the overturning failure, and it's a type of failure analogous to the overturning of the conventional retaining wall. It is assumed that an active wedge develops and full wall friction is mobilized along the back face of the reinforced earth mass. And this failure mode implies that distortion of the reinforced earth mass occurs, or in other words, internal failure by slippage of the reinforcement takes place simultaneously. In the standard design of reinforced earth walls, it is considered sufficient to show an adequate safety factor against slippage of the reinforcement in order to exclude the possibility of the overturning. Okay, so in the second page, it shows the typical reinforced earth wall. So you have a reinforced material like strips here, right? And that's spaced in inserted at the even spacing, regular spacing. And Q, maybe you have some structure or the road or some pavement, and also there are some depths. So this wall is inserted to the subsurface to a certain depth, which is about 10% of the total height, and the length of the reinforcement to be inserted is about 80% of the total height. And you may use the steel face element, and you may use the concrete face element. For the inserted strip or the reinforced material, you can have some smooth strip or the ripped strip. And surely this will give you more friction because of the hump here. So the example of the external failure. So here the deep city failure and bearing failure and sliding failure and overturning behavior. So deep seat failure shows that it's more like a slope failure, right? You have a kind of failure plane developed. Right? The bearing failure is that when you have a high stress from the surface, right? This is more like a foundation, shallow foundation, the case of the shallow foundation. And the sliding failure is like a conventional retaining wall sliding movement, right? So you have a sliding, and this is the frictional resistance, right? Fr, right? And driving force Ft. And the overturning is when the wall is moving this direction with the toe is fixed. So you can check both sliding and the overturning by examining the moment here. And each failure will have different factor of safety criteria. Typically, factor of safety 2, for this bearing failure, factor of safety larger than 2.0 is used, and for the sliding failure, the factor of safety larger than 1.5, and for the overturning failure, factor of safety larger than 2.0 is used to check the external stability. And the second mode was the internal failure mode, right? This is the case where the failure takes place by the rupture of the reinforcement, also referred to as the tie break, and failure takes by the slippage between the reinforcement and the surrounding soil, also named by tie pull out. So you get the idea. And the rupture also can occur, and excessive deformation or buckling of the face element or failure of the connection. So these are the typical failure mode that people observe in the this reinforced earthwork. And here shows that some picture about the failure mode. The rupture can occur at the you can see that along the failure line, these or the strips were broken, and the slippage of the reinforcement is that along this failure line, if the soil moves, then this whole reinforced material can be pulled out. So, and you can have some local failure at the connection, or the buckling of the face element, or the failure at the connection, and excessive deformation. So this gives you some idea that what are the failure modes that can occur in the reinforced earthwork. Okay, next up is the design procedure. So in general, the procedure is as follows. First is you select the granular backfill, and for the selected granular backfill, you define or find some properties of this backfill material, and using that you can check the external stability and the internal stability. So the selection of granular backfill is very important, because in general, typically in this area, the reinforced area is filled with the backfill material. So it's a soil type 1, and this will have maybe friction angle and the total density or the cohesion. Right? Or if it's cohesionless soil, then there is no cohesion. But and then you have also another soil, maybe indigenous soil, soil 2, which will have different friction angle and the density, or the void ratio. And also at the bottom, you have a subgrade soil. And subgrade soil will have also different properties. So by selecting, after you select this backfill material, then you define and you find this friction angle and the density and some other maybe the interfacial friction between this soil and the strip, or the tensile strength of this material, etc., etc. Also, you will have to find out what will be the regular spacing for this backfill material. So delta B and delta H. So first procedure is to select the granular backfill material, and it follows the guideline given as selection criteria, and the primary purpose is to ensure the development of the friction. So if the friction is too low, then it will not give you the full resistance. So the reinforcement effect will be reduced. So the higher friction will be better. And the second is the free drainage. So that the water can drain easily, not accumulating the excess pore pressure. So the table 18.1 gives you some standard, show you there are some standard backfill criteria, and here the reinforced earth, this is the typical criteria, and the grain size, it gives you some idea about the grain size distribution. So maybe like 0.7 millimeter, less than that, it's just 15% is recommended. Generally, the fine fraction less than 15% is recommended, which is because we need to ensure the free drainage condition. Right? If the fines are too much, then permeability will be too low. And backfill is placed and compacted at the dry side of optimum. to ensure the free drainage, right? And also to increase the friction factor. So the friction factor recommended is the tangent delta larger than 0.3 or the delta larger than 17 degree. And for the backfill criteria, the resistivity and the pH range is suggested. This is because to avoid the excessive corrosion between of the reinforcement material. If the reinforcement material is metal, then you have to be careful about the corrosion issue. Right? Okay. Once this granular backfill is selected, then you can check the external stability by calculating the factor of safety for overturning and sliding and bearing capacity failure and the overall slope stability. And then you will check the internal stability for the soil reinforcement bond, so for the pull out or the rupture failure. So this is the slippage failure. And check the tensile stress in the reinforcement by looking at the rupture failure. And there's one more handout showing you the guideline for the selection of backfill material. So you can just refer to this table for your reference. In the next class, we're gonna explore the how to examine the external stability and the internal stability by using some examples.